Suppose a large bag of Reese's Pieces has 1,000 pieces. The manufacturer says that exactly 40% of the candies are orange. If we select a random sample of 50 pieces, how many will be orange? Number one, let X equal the number of orange candies in the sample. Explain why X is a binomial random variable. Explain why X is a binomial random variable. It's binary. What do we have to check if we want to know if it's a binomial random variable? Bins. So let's go through and check that. You said it's binary. So if it's binary, you should be able to tell me what is success and what is failure. Success is getting an orange candy. And failure would be not orange or any other color. Okay. When we're checking bins, what is the I part? Independence. Now, I noticed something happen when I was looking at people checking for binomial random variables on the test. We are 99% of the time not allowed to assume that things are independent. And in this case specifically, because I'm taking orange candies out, is it actually independent? No, when we sample without replacement, it's not truly independent, but what can we do so that it's basically independent? 10% condition. So what would I do to check my 10% condition here?
10% of the total population, which is all of the large bags of Reese's.
In this case, we've got 1,000 pieces. We're not looking at all. Yeah, so 10% of 1,000. How big is our sample? Is 50 less than or equal to 10% of all of the candies in the bag? Yes. So we're doing it without replacement, so technically not independent, but we get approximate independence here. When you go to talk about the independence condition, I have to see your 10% condition unless we are sampling with replacement. If it's sampling with replacement, then you don't have to check the 10% condition. What does N stand for here? Number in our sample. What is the number in our sample? 50. Please make sure that you are writing down little n equals 50. Don't just put 50 when we talk about number of trials. Little n would be our sample size. Make sure you're writing that down. And then what does S mean? You could think of it as success. It'd be the probability of success. We need the same probability of success each time. 40%. Yep. So P, which is the true population proportion, is 0.40. All right. Here's where I need you to grab your phone or your tablet or your computer. We are going to take some random samples. So if you have a computer with you, turn it on. If you have a tablet with you, open it up and navigate to Canvas. If you're doing this from your phone, same thing, navigate to Canvas for me. Once you get to Canvas, go to Modules and look for today's date in Modules and click on that. I want to make sure everybody's got this. When you get to Modules and you go to today's date, there's a link underneath task number 2 that I want you guys to click on. Yep, that's it. Right, I'll come right back to this screen, okay? I'll come back. No, that's okay. I'll come back to that screen. All right. Again, if you haven't already, you need to navigate to Canvas, This link right here where it says Rossmann Chance Applet Collection. We're clicking on this and it takes you to a page that looks like this. Little candy machine full of Reese's Pieces. We are going to take a sample. What did we say the true proportion of orange candies was? 0.4. So we need to change this right here. It says 0.5. When you load the page, I need you to change it to 0.4. And we said we're going to take a sample of how much? 50. So I need to change that 25 to a 50. And we're going to draw one sample for right now. So we're going to draw the sample. When I hit that button, my little candy machine starts to go. The animation is super cool, isn't it? All right, so it's sorting them into orange and not orange, and then it tells you, says the most recent number of orange candies. Whatever yours says, write it down underneath number 2. I want you to take 5 samples total. So you're going to do this 5 times. You can turn the animation off if you want to. It'll go faster if you don't want to watch the whole animation. You're welcome to. I want you to take 5 random samples and write down for each sample how many orange candies there were, which it tells you right here. Take and write down how many orange candies you got. Five random samples, write down how many orange candies you got. Come and start copying yours down. So you got 24, 13, 15, 21. No, you're fine. And 24. Awesome. All right. Do you have yours? Still working on it? Oh, no. Yes. Okay. All right, you had 18, 23, 17, 17, and 21. Right, do you have your samples? 20, 23, 25, 16, and 20. $15, 20, 22, 24, and 16. 27, 19, 18, 19, and 20. Awesome. What'd you get?
19, 11, 18, 20, 22.
All right, 19, 11, you said 18?
Yeah. 20,
20,
and 22.
And 22. 28, 20, 16, 24, and 25. Please start copying this into your notes. Are you writing yours down? You're supposed to be writing down your samples. What it's saying right here. You want to write that number down. You're going to write that. You're going to do this 5 times. So your first one is 23. Your next one is 23 again. What's your third one? 18. Fourth one is 15. Please make sure that you have written down what your random samples were, and then 19. You are going to need these numbers again. Is that 29? 29, 23, 20, 19 and 19. Okay. 17, 18, 18, 17, 18, 18, 29 and 18. 29 and 18. All right, just a few more to go. Please make sure you are getting this dot plot into your notes. 21, 15, 22, 19 and 19. Is that 24?
Yeah.
Okay, 24,
21,
21,
25, 17.
25 and 17. Okay, fair enough. Anthony, do you have yours yet? Working on it. What? No, you're way overcomplicating this.
Okay.
Up here, 0.451. Let's turn off the animation. Draw a sample. There you go. Your first one is 23.
My second one is 19.
19.
My third one is 17.
17.
My fourth one is 18.
18. And your last one?
17.
17. Did you write all those down? Because you need those numbers. If you look at the dot plot, you can copy it down from there. Get your 5 numbers. All right. This dot plot that we just created is a sampling distribution of x, of our random variable x. This is a sampling distribution of x. What does each dot represent here? A trial. So what was a trial in this case? In a sample of 50, yes. So each dot represents one random sample of 50 candies and the number of orange Reese's Pieces that are in that sample. Every single dot represents one random sample and however many orange Reese's Pieces were in that sample of 50. How do you calculate the mean for a binomial random variable? N times P. So what would the mean be here? Not the mean for the sampling distribution, just the mean for the binomial random variable. What is N times P? Louder. Yes. 50 times 0.4 is 20. I'm going to leave this up for just a moment. How do we calculate the standard deviation for a binomial random variable? All underneath? A square root, yes. N times P times 1 minus P, all underneath the square root. Go ahead and calculate that. You're going to write both the mean and the standard deviation underneath number 5. Both the mean and the standard deviation. Write it down for number 5. I'll put my answer up here in just a second. I just want to make sure everybody had a chance to get the dot plot copied into their notes.
What notation is it? X bar?
No, these are, so this is a number of candies. So this is for X. X bar is when we take a group and we calculate the average. Yep. Great. Does anybody need me to leave the dot plot up longer? All right, I'm going to scroll to the next screen then. We said the mean was 20 because we do N times P. For standard deviation, you guys already told me how to calculate that. Square root of n times p times 1 minus p. What do we get when we do n times p times 1 minus p underneath a square root? Grab a calculator if you need to. Cell phone calculator can work here.
12 or 1.2, one of those.
Did you do the square root part?
Oh.
3.46. Yep. Square root of 50 times 0.4 times 0.6, so we get 3.464. If you did 3.46, that's fine. To find the approximate shape, we are going to check our large counts. Do you guys remember how to check large counts? We want to make sure that our number of successes are at least 10, and our number, sorry, not successes, number of expected successes is at least 10, and number of expected failures is at least 10. We have to make sure that we're big enough. So what is my expected successes here? 20. N times P. So that's the first thing we check. N times P is my mean at least 10, is my expected value at least 10. And then how would I check my expected number of failures? 1 minus P. So I would do N times 1 minus P. What's that going to come out to? If I have 20 expected successes and it's a binary choice, how many expected failures would I have?
35.
Not 35.
3.5.
Not 3.5.
350.
Guys, there's two options here, success and failure. How many trials do we have?
Oh, 40. No, 30.
I was thinking.
We're not doing standard deviation here. No standard deviation. If I have 20 expected successes, 20 orange candies,
Isn't it
30 to
4
fail.
times?
then we're going to expect 30 failures because we have 50 candies total. 1 minus P, so 50 times 0.6.
I don't know. I didn't write it wrong.
7 from.
If we pass the large counts, what is the approximate shape? Normal. It is approximately normal. I want to sketch it now. So draw your normal curve. Draw your bell-shaped curve. What would go right down the center of the bell-shaped curve? The mean, which is? What is our mean? 20. Then I need a big capital N next to it to show that this is supposed to be normal. Helps when my art skills are bad.
That's like a perfect bell curve.
She traces it.
I trace them.
Oh.
I'm really bad at these.
I want to see you
I
draw
trace
one.
them.
I want to see you draw one because you always say this and don't do purposely. Oh.
I'm very bad at these.
No, we all are.
That's why we put the big capital N next to it. So no matter how bad you are at drawing this bell-shaped curve, everybody can understand what you were intending to draw.
I'm surprised. You know, I'm honestly surprised. You know what you need to do? You need to draw. You need to just express it, and eventually you're gonna be able to do it. Practice makes perfect.
Practice makes perfect. That's why I trace it. What would go next to my big capital N?
The mean standard deviation, 20 and 3.5.
Above the mean sign, which is whatever.
Yep.
I can't remember.
Mu.
I am
And what else?
And 3.464 above the standard deviation
Keep yourself
symbol.
safe.
Perfect.
Sigma.
Sigma. Perfect.
Keep yourself safe.
Fantastic. All right. Do you guys have any questions so far? So far, everything that we've done on this side has technically been review from the last chapter. We checked to see that it was a binomial random variable. We found the mean and the standard deviation. We determined that it is approximately normal by doing our large counts. So now, on page 10, instead of finding the number of orange candies, I want you to find the proportion of orange candies. And I want you to use the same sample that you did before. That's why I had you write all those down. So use your 5 samples from number 2 and turn each number of orange candies into the proportion of orange candies in the sample. So these are all going to be p hats. You're going to have p hat equals, write down your decimal. And then you're going to have another p hat equals, and write down your decimal. How are you going to turn these into proportions?
You're going to take each one of your numbers and divide it by the sample size. So 17 divided by 50 for me.
Yep, you're going to divide everything by 50. So please go through and do that to all of your numbers. Take all of your numbers from your original random sample, divide it by 50 to turn it into a decimal. Take every single number that you got from your original random sample, turn them into decimals by dividing them by 50.
I have a stuffed rose and an itchy throat. That's a cold, right?
Typically, yeah.
I think with the weather, it could consider a cold. That isn't transmittable, right?
I mean,
Yeah.
I work with
Most of
children.
them are.
Should I go into work?
No.
Tell
if
me
you just
no.
have a cold, you'd be fine.
Okay.
If you start to run a fever,
I
then
don't
no.
feel I have a fever.
Wear a mask.
Yeah, I was going to say you should wear a mask.
I think the rule for me is once I start like having vertigo, that's when I write down. Like when you start to
You have your proportions? Awesome. That is 0.48.
I only had that once with a fever. I was like, this is great.
No, my worst day
Oh
was
no, my head's starting to hurt.
was the day that we had that.
All right, I'm going to come around and get your proportions, and we're going to make another dot plot. 0.48, 0.48, 0.26, 0.3, and 0.42. All right, you got 0.34,
Oh wait, no, my brain.
0.34, 0.36.
So it's just hundredths place.
0.38.
So 17, add a decimal.
Is this last one 0.46?
Yeah.
Okay.
Add a decimal, and then multiply that number by 2. Because 50 times 2 is 100.
How does that make sense to you?
I get it. But
17 over 50, multiply both by 2, it's now
46.
34 over 100. So now it's 0.34.
34,
My brain just
34,
immediately skips that.
42,
So I just immediately
0.4,
2 times the number. And
0.46, 0.5, 0.32, and 0.4. All right. Guys, I do want you copying this dot plot into your notes, please. 0.3, 0.4,
I'm glad I can't smell.
0.44, 0.48,
Thank you.
0.32.
Enjoy your presents.
Copy this into your notes. Can you flip the page? That's okay.
Oh wait, I put them all on here.
Oh, you got your proportions in here. That's fine. 0.54,
0.38.
0.38,
0.36.
0.36,
0.38 again.
0.38,
0.40.
0.40. All right, you have 0.38, 0.22, 0.36,
0.4.
0.4,
0.44.
and 0.44. 0.56, 0.4, 0.32, 0.48. You said the last one was 0.5? Perfect. Guys, I need you copying the dot plot into your notes. 0.46. 0.46. 0.36. 0.36. 0.3. And 0.38. Thank you. 0.46. 0.4. 0.38. 0.38.
Am I supposed to write them all right here?
Yeah, it's fine if they're down there. I don't care if they're on the line or not. Okay, so you had 0.36.
0.34. Where's the real leaves?
You had 3.36s. 2, 4, 6, 1, 2, 3, and then you said 0.34 and 0.58. All right, and you had 0.42, 0.3, 0.44, 0.38, 0.38, 0.48, 0.42, 0.42, 0.5, and 0.34. All right, there's our scatter plot. Or sorry, not scatter plot, dot plot, my bad. There's our dot plot. This is the sampling distribution of what? Are these numbers of orange candies still?
Proportion.
These are proportions. Did they come from the whole population?
No.
No, they came from a
Sample.
sample. So what symbol would I use to show that it came from a sample?
P hat.
P hat. This is the sampling distribution of P hat.
Since now.
So what does each dot represent here?
Probability
Proportion per trial, a trial's proportion.
Yes, let's use a couple more words, but yes. Like, be as specific as you can.
A trial of 50 Reese candies.
Mm-hmm.
The proportion of a trial of 50 candies?
Someone help me out.
No, that's okay. You've got all the words, but they're just kind of jumbled together. So each dot represents one trial, right? One sample of 50 candies. And then we calculated the proportion that were orange in that sample. So one sample of 50 candies and the proportion of orange Reese's Pieces in that sample.
You said I had the right words just.
Yeah, you had all of the right
like
words.
7 words, like.
All I did was turn it into a sentence and put the words in the right order.
No, because it doesn't, there's too many.
There's too many things happening. Like, sample circumstances and the proportion of one species.
Yes. What I want you to do when you are trying to figure out what each dot means, think about how you got the number to make your dot. What did you actually do? Because that's what you're going to write down. You took a sample of 50, and then you found the proportion. You turned it into a fraction by dividing by your total. And it was the fraction of orange, or the proportion of orange. Question. I'll come right back to this screen, but how does this dot plot compare to this dot plot?
Wait. It's this way. It's about the same.
It's, yeah. It has the exact same shape. Does it have the same mean?
Wait.
And
19 over 51 is the same thing. 19 over 50.
Mean over here is like 19.
Over there is 19.
Over here, the mean is 19. Here, the mean is 19 over 50.
0.38.
So is the mean exactly the same?
I still say
Yes.
So they're measuring different, no.
They're
asking
measuring different
questions.
things. They're measuring different things. But it does have the exact same shape. It does have the exact same shape. So when we did the mean for our binomial random variable, we did n times p, right? How would I calculate the mean for this distribution? And I'm not just talking about finding the middle of our dot plot. What would the mean for this distribution be? Let's go back and look at this one. We said our expected value was what here?
Not 20.
20 was our expected value. My distribution seems to be centered more around 19, but my actual true mean is 20. Is this an unbiased estimator? Yeah, this is not a complete sampling distribution, so I would expect to be close to, but not exact. So here we're centered, expected value is 20. So what would my expected proportion be then? 0.4. So finding the new mean, 20 divided by 50, 0.4. It's just p. My expected value, my mean of p hat, is just the true proportion, p.
So nothing changes.
For standard deviation, what did we do to calculate standard deviation before? NP times 1 minus p, all underneath the square root, right? But then we're calculating a proportion, so then what would I do to that? By? By 1,000? By 50. We're going to divide by our sample size. We took our expected value from before, we divided it by 50. That's how we got 0.4. So here I would take my standard deviation from before and divide it by 50. Nope, thankfully not. What is 3.464 divided by 50?
6.928.
Yep. I did 0.0693. So let's talk about how we can do this in a formulaic way, something that I can write down on my formula sheet. These are on your formula sheet, by the way. The mean of p hat will be just whatever p is. For standard deviation of p hat, we did n times p times 1 minus p underneath the square root, all over n. But do you see how I have an n here and an n here? The square root's only over the top, though, right?
Yeah.
So if I wanted to put the bottom also underneath the square root, what would I have to do to it?
Square root.
Not square root it, but I'd have to square it so that when I square root it, it comes out to be just n. If I want to put it underneath the radical, if I want the radical to come all the way down, then I would have to square that so that when I square root it, it's n.
Oh, okay. No, I understand it now.
But then when I write it like this, do you see how I can cancel out the n up on top?
Yeah.
All right. So this is my formula for standard deviation when I'm talking about proportions, p hat. We do the square root of p times 1 minus p over n. You get this formula and this formula on your formula sheet. What is the approximate shape of the sampling distribution? What'd you say? How would I check to see if it's normal? I do think it's normal. How do I check?
Bins.
Not bins, that checks to see if it's binomial. Check, look at what we did on the other side. Large counts. So how do we check large counts?
Is it bigger than 10 for both?
Is it bigger than 10 for both? Is what bigger than 10? You're right.
Is the mean and standard deviation, no, the mean and the opposite of the mean, the inverse.
So I still have to do n times p because I still want to make sure that my number of successes comes out to be greater than or equal to 10. When I'm talking proportions, when I talk about proportions, I'm never going to have a proportion that's bigger than 10. Because a proportion is just a fraction or a percent, and my percents can't ever go over 100% or 1. So checking my large counts, I still do n times p, and n times 1 minus p. What is n times 1 minus p here? What would that come out to be?
Um,
30.
30. Are they both at least 10?
Yeah.
So what is my shape?
Normal.
Yes. Approximately normal, technically. Approximately normal. Do you guys know the symbol for approximately, the 2 wiggly lines?
Yeah.
You can write that with normal instead of writing out the word approximately. We know that bags of Reese's Pieces contain exactly 40% that are orange. If I select a random sample of 50 candies, what is the probability that the sample proportion, what's another way of saying sample proportion? P hat. What is the probability that the sample proportion, P hat, will be 50% or greater? So let's walk through this a piece at a time. We said that this was shaped approximately how?
Normal.
Approximately normal. So what do you need to do? Draw a picture. Draw a bell curve. What should go right down the center this time? What is my mean this time?
No.
0.40. 0.40 goes right down the center. I need my big capital N next to it with my mean and my standard deviation. And then I want to know what's the probability that it will be 50% or greater. Is 50% going to be left or right of my mean? It's going to be on the right. And I want 50% or greater. So I have 0.50 somewhere to the right because it's bigger than 0.40, and I've shaded it to the right. So there's the picture describing what I'm going to find. Now we need to write this out with notation. And this is where I just love statistics because we reuse stuff. What notation do I use when I want to talk about probability? P, big capital P with parentheses. So I have a big capital P with parentheses. And I want the probability, I'm going to read this sentence right here and figure out how to change it into a probability statement. Probability, capital P, that the sample proportion, which we said was P hat, will be 50% or greater. 50% or greater. Less than or equal to? Greater than or equal to what? 0.5, yes, or 0.50. So here's my probability notation. Again, I just took this sentence right here and turned it into symbolic notation. Probability that the sample proportion, P hat, will be 50% or greater than or equal to 0.5. How am I actually going to calculate this now? Normal CDF. What's my lower bound? 0.5. Upper bound? Something stupid big. 1 million. Sounds good. 0.4 for the mean. Oh, sorry. 0.4 for the mean. 0.693 for the standard deviation.
Because the standard deviation is so low, is it fine if we do something like 10?
For your upper bound?
Yeah.
Yeah. Technically speaking, because these are proportions, these are like percents, 1 would be a perfectly fine upper bound here because we can't go over 100%. We can never have a proportion that's more than 1. All right. So go ahead and do this for me. Calculate that out.
Oh, no, wait, really? I should call it Sure.
what did you get? Zero, I got, can I say it?
Yeah.
0.0745.
I love it. 0.0745. All right. I want to look at the quick notes real fast. We're going to hold the check your understanding until tomorrow. So today's lesson, do you notice how it was front, back, front? And tomorrow's lesson is another one that's front, back, front. We didn't get all the way done with today's lesson. So I'm suspicious about whether or not we will get done with tomorrow's lesson by the end of the day tomorrow. So how about we say that new homework? Monday we come back from break.
Whoa, actually.
Now, hold up.
Oh, we could do it.
We need to just finish whatever tomorrow's lesson is on Friday. So whatever we don't get through tomorrow, we'll finish on Friday. We won't push into new stuff. And whatever time we have left over, you guys will have to work on the homework and ask questions. So hopefully you can get it done and you don't have to worry about it over break.
Okay. And then it's kind of like a refresh of stuff that we come back.
Right? Okay. Real quick, with my last 1 minute here. Sampling distribution of p hat. To check to see if it is approximately normal, we do n times p and n times 1 minus p, just like before. The center is just whatever p is. The standard deviation, square root of p times 1 minus p over n. Now here's something to keep in mind. If you are sampling without replacement, you have to check your 10% condition. If you are sampling without replacement, you have to check your 10% condition. None of the questions will prompt you to do that. You have to know. If it asks what is the standard deviation, the first thing you have to do is check the 10% condition, because if it doesn't meet, you can't calculate it. All right? That's where we're stopping for today. We will finish up the check your understanding tomorrow, and then we will do the next lesson. You will need a computer or a tablet tomorrow. I can get it to work on phones mostly, but if you have a tablet or a computer, please bring that with you to class tomorrow. It's so much easier with a tablet or a computer.